Hello, everyone. Welcome to Lecture 5 of the Mechanical Design course. Today, we're going to go over materials and manufacturing. What will we cover in this lecture? First, will be material properties and what they are. Then, we'll go over metals, plastics, wood and composite materials, and then general manufacturing tips. Material properties. What are material properties? The specific properties of each material determine the applications where they are best utilized. In engineering, we have to balance the many properties of materials in order to choose a best fit. While there are thousands of properties important to everyday engineers, FRC applications mainly care about a few. That's lucky because there's quite a few very complicated properties that we can just skip over. So the types of properties we'll go over today are cost, ease of manufacturing, strength, weight, flexibility, and hardness. Cost. This is arguably the most important property in FRC and engineering. This determines whether or not we can use a material, as all teams or corporations or companies have a limited budget. We could try to use the newest materials coming out of NASA or MIT or UC Berkeley or wherever. Most of the time, we will not be able to afford them, so sadly, we cannot. We must find the best fit material within our budget. So the first and most important thing we have to care about is the cost of the material. And then we look at what is the best material we can use to fit that cost. Next, ease of manufacturing. How easy a material is to manufacture. This is also essential somewhat at cost. Some materials are easy to manufacture using cheaper tools such as wood, plastic, while others, like carbon fiber, are difficult to manufacture with. There are also manufacturing methods that can only use certain materials, such as 3D printing and laser cutting. This is especially important in FRC as we can't just buy any machines. We have to use what we have. If a machine cannot cut a material, then we cannot use that material. Strength. The strength of a material decides whether it will break or deform during its use. Material strength can typically be understood through the concepts of tension, compression, and torsion. Tension is a force that stretches a material. So, for example, if you had a rope and you were to pull it apart from each other, that rope would be under tension. Compression is a force that shrinks a material. So if you got an item and you were to squish it and it starts deforming, that will be under compression. Torsion is a force that twists a material. The ability to withstand these forces without deforming can determine a material's best uses. So deformation is when you stretch it or compress it or twist it and it won't go back anymore. It's permanently deformed. Weight. The weight of a material is also very important in FRC and engineering. In the case of FRC, a robot with heavier materials might go over the weight limit and will also sometimes suffer from less speed. However, heavy materials can be useful to bring the center of gravity towards the bottom of the robot. Another example in engineering is aviation. In airplanes or spacecraft, you want to use very light materials in order to save energy. Flexibility. A material's flexibility determines its ability to both withstand impact and to form a desired shape. Materials that are highly flexible are appropriate for parts that will encounter large impacts, as the flexing will allow it to disperse the energy over more time. However, flexible materials also suffer when used as a support. So to the right here, we see an image of a greenhouse where they use polycarbonate sheeting, which is a very flexible material we'll learn about later, in order to make walls of this odd shape. If the material wasn't flexible, this would not be possible. Hardness, a measurement of how much a material resists deformation. In FRC, this is mainly important for grip, as a material such as rubber deforms more. The grip it has increases. We measure hardness in rubbers and plastic with durometer. A higher durometer equals less deformation. So in FRC, the only real purpose we'll care about durometer with is its wheels. And essentially, the more grip you want, the lower durometer you want. You'll see this when you're buying the wheel. Any questions? Okay. So what now? Now that we understand the basic properties of each material, we can now understand each material's utility in each case. Now we will go over a plethora of common materials we use in FRC, their properties, their use cases, and their manufacturing processes. We will sort them into metals, plastics, woods, and composite materials. First, we'll go over metals. The basic properties of metals are they are conductive, which means that electricity and heat can flow through them easily. This is important because we might accidentally short circuit robots using conductive materials. They are also generally expensive. This is compared to the other materials we'll list here. They're also very strong. This is their best quality. They're very unlikely to break. They don't snap as much. They're really good for strength. They're basically the structural material of FRC. If you need structure, you typically use metal. However, they are also more difficult to manufacture with, at least compared to plastics and wood. They are also hard, which means they're not easy to deform unless they're under heat. So typically, they will stay in the same shape, even if they flex a little bit. Types of metals in FRC. So first we'll go over aluminum, and there's two types of aluminum we'll go over. They're two alloys, 6061 aluminum and 5052 aluminum. They're both very common, and they both have their purposes. Next, we'll go over steel. And after that, we'll go over titanium, which I put an asterisk here because titanium is not really something we use in our own team. We mostly use it when we buy it from off-the-shelf parts. We'll go over why later. So first we have aluminum. The general properties of aluminum are they are moderately expensive, they're lightweight, they have above average strength, they have average flexibility, they're hard, but less hard than other metals, so they're slightly easier to deform, and they're the easiest metal to manufacture with. So the most important quality here is that it's lightweight and it's strong. The main purposes of aluminum are when you have to have some sort of lightweight material that can also hold its strength. And in FRC, that's very important because we have our weight limit. So that's why aluminum is so popular and arguably the most popular material in FRC. So now we'll go over 6061 aluminum alloy. This is the general purpose alloy of aluminum. The reason why is that it's very strong and it's good for plates, extrusions, and box tubing. These are very popular in FRC, and this is why we mostly use it. It is also the most commonly used in the industry, especially for things like aircraft and spacecraft because of its strength properties. However, its flaw is that it is slightly less flexible than other alloys, which is why we mostly use it for plates, extrusions, and box tubing because we don't have to bend them. This is the most popular alloy in FRC. The next alloy is 5052. This is the one you want to use when you're bending aluminum. So if you want to make bent sheet metal, this is the one to use. This is very rarely used for extrusions and tubing, and whenever you're trying to buy them, it's very hard to find them in 5052 alloy. That's because it's less strong, and it also has a better surface quality than 6061. So 6061 alloy has slightly worse finish on the surface. So if your goal is to have really shiny and nice looking aluminum, you're better off going with 5052. This is slightly harder to cut than 6061, and it's slightly weaker. This is why teams typically use them less for structural reasons. However, it is also cheaper than 6061. Not a lot cheaper, but slightly cheaper, and that can make a difference. Manufacturing aluminum. Aluminum can be cut and drilled relatively easily compared to other metals. It can be easily cut with a CNC router or mill. The trick with aluminum and most metals is to keep the heat down, as they are good conductors. So what I mean by this is that the conductive material will cause the heat to spread. They'll start melting the material. It's really bad. You want to make sure, do everything you can to keep heat to a minimum to make the manufacturing process better. So in order to do that, we use drill bits for metal, preferably out of cobalt. Keep the speed relatively low, so the rotational speed of the drill bit, keep it lower than you would for other materials, and use a lot of lubrication. So most of the time, this would be like some sort of cutting fluid. Also, aluminum is generally not great for welding. If you do weld, use 5052 aluminum because 5052 is actually weldable and it's much better for it than 6061. If you're ever welding aluminum, you should always be using 5052. Also use 5052 when bending aluminum. especially when using a bending brake. Its just properties better support it. You can make tighter angles. It's less likely to snap. It's just better for bending. Also, when you're manufacturing, be mindful of aluminum shavings. We'll go over this later, but it's important to not breathe them in, to use gloves when handling parts with shavings all over, because they will cut you. Just be careful of them. So here's the forms of aluminum. Aluminum is often shipped in sheet, extrusion, or tubing, which can be box or circular. These different types of all have different uses in FRC. Sheet aluminum, most versatile form of aluminum. This can be easily cut into plating and bent. However, it suffers from less torsion strength without further manufacturing design. Essentially, when you just have a plate or sheet of aluminum, it's very easy to kind of twist it. Typically, it's strong in one angle, but not strong in the other angles. That's what the next two forms are meant to fix. However, this is most versatile. You can turn this into almost any shape. You can bend it. You can use bolts and spacing to make different shapes with them. Really good for like gearboxes, because especially custom ones, because you can just make siding for it and cut it out. However, it is, once again, the least strong out of all of them. You have to do manufacturing to make them strong. Extrusion. This is the most constricting form of aluminum. However, it is also the easiest to prototype with. The special slots allow for easy construction with bolts and nuts. So when you put the bolt head into the slot and you tighten a nut with some sort of plate on the outside of it, it can just slide on and slide off really easily. These are also structurally strong because of the shape of them. However, they can be heavy because they have a lot of metal that doesn't need to be there if you use other forms. Extrusion is best used for prototyping. Aluminum tubing. This is the common middle ground of aluminum. Tubing comes in many shapes. They have circular shapes. They also have 2x1, 1x1, and more. This is the best for making a robot frame and gains a lot of torsion strength compared to sheets. So last year, this is what we mainly used in AvengerRobotics because it's very relatively easy to buy, easy to manufacture with. We don't need to use a CNC. It's great. A lot of strength. We can make frames with it, and then we can put sheets or plastic or wood and just make things out of it. Next, we'll go over steel. The general properties of steel are that it is extremely strong, it is cheap, especially for a metal, heavy, not flexible, extremely hard, so it's not very malleable, and is more difficult to manufacture than aluminum. Why do we use steel? We use steel mainly for hardware, so bolts, nuts, gears, washers, etc. Basically, anything that is small and needs to maintain its shape for a very long time. This is because it is stronger and less likely to wear than aluminum. We also use steel as a ballast, or a weight for balancing, as the metal is cheap and heavy for its size. So if we need to add a lot of metal to the bottom that is heavy, this is the one we use. Most of the time when we're using steel in FRC, it's just we're buying it from some sort of shop. And we'll use steel mostly to make ballasts, which is just cutting it with the CNC into a certain size and putting on the bottom. Steel manufacturing. It can be manufactured similarly to aluminum. Heat distribution and bits are extremely important, even more so with aluminum. Keep speeds low and use a lot of lubrication. Steel is also really easy to weld. So if you want to weld parts together, you're much better off using steel than aluminum, as long as weight is not a factor. In general, if a steel part requires precise machining, buy it off the shelf or use a specialized manufacturing company. What I mean by that is that steel is much harder to manufacture. If you need it to be precise, you need to be well cut, you're better off just having someone else do it for you. If your team wants to manufacture steel in-house, try investing in a CNC mill, not router, and a water jet, as these will allow steel to be a lot easier to manufacture. CNC mills allow for more angles to cut, and typically they work at slower speeds that are meant for metal. CNC routers are used more for other applications. And water jets use high pressure water to cut. Titanium or other metals in FRC. Properties of titanium is they are expensive, expensive, expensive. It is very expensive. You don't want to buy it. They are expensive. Remember that word in your head when thinking about titanium. It is expensive. It's also very strong and very hard, similar or better than steel. So essentially, it is stronger and less malleable than steel is. It is also lightweight like aluminum. It is basically the perfect metal. However, titanium is very difficult to manufacture with, and therefore should mainly be used with off-the-shelf components. For example, the popular swerve drive modules typically use titanium in parts of it. Any questions? Someone asks, in your research, did you find out why they're called 6061 and 5052? Who decided on numbers? No, I did not specifically figure out why they're called 6061 and 5052. I will try to get back to you about that. That is actually an interesting question. It's probably something to do with the exact metals inside of it. Let's go on to plastics. The basic properties of plastics are that they are cheaper than metal, not conductive, so they don't conduct electricity or heat. They're lightweight. They're average manufacturing difficulty, so easier than metal, but could be easier. And they're not very strong. So they're, easy to pull apart, easy to compress, then they're going to break pretty easily though. The types of plastics in FRC. So this time I decided to split them into groups. So the first group we have is plastic sheets. The two sheets we have here is polycarbonate and acrylic. The next group is 3D printing filament. So I split this up into PLA, ABS, and nylon. There's more than this, but these are the three I think are most important for robotics. Plastic sheets. Why use plastic sheets? These are used when you need large and simple parts made out of plastic. Depending on the exact material, these can be used to support electronics because they're non-conductive, be used as structure on ultra lightweight parts, and can be used on parts that need to absorb impacts. The two types of plastic sheeting in FRC is polycarbonate and acrylic. Polycarbonate. Polycarbonate is the most used plastic in FRC. Its special property is its impact resistance and flexibility. It can be bent and returned back to its original shape, and therefore is good for parts likely to face impacts. For example, intakes or outtakes likely on a robot that go outside of your robot frame and bumpers, which might hit a wall or another robot. You want to make them out of polycarbonate because they're very unlikely to break at that point. However, it shouldn't support a heavy structure, especially in the angles where it's most flexible. The flexibility makes it so it's very impact resistant. It just cannot hold up heavy things very well. Manufacturing polycarbonate. Polycarbonate can be manufactured easily using wood bits on a CNC machine, any saw for wood, and a drill press. It is relatively soft and reacts well to tools made for wood. However, due to the way it's made, it cannot be used in a laser cutter. So essentially, just don't use polycarbonate in a laser cutter. It won't work. Acrylic. Acrylic is a material with a very niche usage in FRC. It is stiff and not very impact resistant. This is similar to glass. Slightly more impact resistant than glass is, but it should be thought of as basically glass. Its main use is for mounting electronics, as it doesn't bend under weight and is non-conductive. Essentially, if you don't want any risk of short circuiting, anything like that, using acrylic as a place to put your electronics is actually pretty good. So the one tip with acrylic is never mix acrylic with polycarbonate, as they are difficult to tell apart visually. The best way I've found is that the sides of polycarbonate has a slight blue tint to them if you look in certain light. Yeah, slight blue tint. That's your look. That's your way of figuring it out. So just don't mix them. The problem with polycarbonate is that even though it's flexible, in large sheets, acrylic also has a slight flexing, so you can't just see if it's flexible. Unless it's like super flexible, you really don't know. Just keep them separate. We've had times in our team where we had parts that were supposed to be made out of polycarbonate, made out of acrylic, and they broke and shattered during competition, and we couldn't replace them. So don't mix them. Manufacturing with acrylic. Acrylic has a tendency to shatter and melt, so be careful to keep heat and speed slower. However, it is softer than metal and should use bits either for wood or plastic. Sometimes on the internet you might find specific bits for polycarbonate and acrylic, and I would use those. If not, wood bits work fine. Unlike polycarb, acrylic can be laser cut. So it actually works really well. So if you have a laser cutting machine or a laser engraving machine, putting acrylic in there works perfectly. If it's big enough, it's actually probably preferable to do that because it's less likely to shatter. So my one tip with acrylic is that always wear safety glasses, especially with acrylic because it can and will shatter. So I have a story to talk about this one. At one point during my FRC tenure, I was in the workshop with my safety glasses on, as you should be wearing, and a group of people that shall not be named were trying to cut acrylic with a miter saw. And the problem with the miter saw is that it's very powerful and it's typically pretty fast. So when you bring the miter saw down too fast with acrylic and you're not properly holding it down, it has a tendency of shattering and having shards of acrylic flying everywhere, which one of them knocked off of my safety glasses. I would be blind in one eye right now if I weren't wearing them. Please always wear safety glasses and be mindful of the shattering. Any questions? Someone asked, can you do the shatter test? Yes, if you want to use materials, you can probably figure it out by just trying to shatter it. However, I don't see the reason why. Just keep them separate. In FRC, acrylic is such a niche material that you don't need that much of it. We just have a small corner where this is your acrylic corner. As long as everyone knows that's the acrylic corner, it should be fine. Any more questions? 3D printing filament. Why do you 3D print? The most complex parts in FRC are often made using 3D printers. They allow for much more complicated three-dimensional shapes. So on the right here, we have this dragon, which, well, I really wish there was a large amount of utility from having an orange dragon on our FRC bot. Sadly not, but you can see how the parts like a dragon could be useful. They're also an excellent prototyping tool, as it is easy to design parts and print them overnight. If you're using SolidWorks or Fusion 360, it is as easy as just exporting it as an SDO file and bringing it to whatever your 3D printing software is. You can bring a part in CAD into a 3D print in less than 5 minutes. However, they are typically used for smaller parts due to limited print space. It's very hard to make very large robot-sized parts with 3D printing. You have to have some sort of mechanism to connect them together. It's not really good. Mostly from I've seen it at the world's competition and in our own team, 3D printed parts are small, mostly like connecting parts. The most common filaments are PLA, ABS, and nylon. PLA filament. PLA is the easiest material to 3D print and is also the most common. However, it has some major disadvantages, especially in FRC. It has lower strength than its alternatives. It can't be easily machined after printing, so sanding it or drumming it or drilling it, it's just pretty difficult. It doesn't do well with that. It also has low heat resistance. It can melt when left in a hot location. If you ever drive with a 3D print, if you have a very hard car, it can melt. They melt. It's very low print temperature. That's why it's easy, but the problem is that it will melt. PLA is best for prototyping or decorative parts. I would put a caveat on this though. If your 3D printed part does not need to be very strong and you just have a bunch of PLA sitting around, you can use PLA. Like if it's a moving part but it doesn't have to be strong, you can use PLA. It's not that bad. Some of these next alternatives might be better, but they have some downsides. Just remember that PLA is always an option. But if you're talking about what it's best for, prototyping and decorative parts. ABS filament. ABS is more popular to use in engineering. The reason why is it has more strength, flexibility, temperature resistance, and cost than PLA. Essentially, when I say cost, I more so mean it's cheaper. The main disadvantage of ABS is that it's harder to print. It requires a high and very consistent temperature, so your printer nozzle needs to go at a higher temperature, and the temperature needs to be consistent, so you cannot have major changes in temperature, otherwise the print is not going to work. And also, more importantly, it can give off toxic fumes. You don't want to breathe that in. So when you're printing with ABS, make sure to print in a very well ventilated room, essentially with a giant wall open to the outside like a garage, or have a fume extraction setup. The fume extraction setup is a lot better because I said earlier, you need a consistent temperature. Being basically outside does not give you a consistent temperature. So essentially have a fume extraction setup and you can print ABS. If not, don't be in the same room you're printing ABS in. Nylon filament, my personal favorite, however, the one I use the least. This is arguably the best filament for use in FRC. It is more expensive and requires a higher print temperature than most 3D printers can handle. However, it is by far the strongest common filament. It has similar properties to ABS, is flexible, is impact resistant, and doesn't give off fumes while printing. Essentially, this is the only 3D printed material in which I would truly trust to be using on very important mechanical parts on a robot. However, it may be overkill for some uses. If you're using nylon for some decorative part or some part that doesn't need to be very strong, I don't know why you're doing it. You're just going through pain and suffering and a lot of money for no particular reason. Tips for 3D printing. Make sure to design a part to be 3D printed. So have little to no large overhangs. Try to have a large flat side to be the bottom. It doesn't have to be the actual pointing down part of the part. However, it just needs to have one large side to print on. Also, avoid internal support if possible. When I mean if possible, I mean if you like going through pain and suffering, put some internal support. If you don't like that, then don't have internal support. Design your part around 3D printing. The more support you have, the more annoying the processing will be, and the more wasted material and time printing. I'll go over more tips about 3D printing in the last lecture. Any questions? Alrighty then. Wood and composite materials. Wood. The properties of wood. It is stronger than plastic, weaker than metal. It is the complete middle material in this equation. It is also very stiff. It doesn't flex a lot, especially when it is thicker. It is very easy to manufacture, extremely cheap, and is pretty lightweight. In FRC, we mainly use plywood, and we rarely use other types of wood, mainly for decorative purposes. Sometimes you might use 2x1 wood for some structural purposes. Plywood manufacturing. We mainly use plywood for prototyping at AvengerRobotics. However, some teams have successfully used wood for their final robot. Some robots that have went to the Einstein competition at Worlds and won have used wood in the past. It is a very common material to make a robot out of. You can also use a CNC router / mill, drill press, any saw for wood. You can also use traditional woodworking tools. Essentially, any tool in your shop besides a plasma cutter or a welding machine can be used with plywood. You can also use laser cutters for plywood. However, I would put the caveat that some of the glue in plywood that keeps the sheets of wood together can cause problems with the laser cutter. I would just say stick with thinner pieces of plywood for laser cutting. So why don't we use wood for everything? So the main disadvantage of wood are its stiffness and its reaction to humidity. So wood does not absorb all impacts well and can splinter or shatter due to its lack of flexibility. Essentially, if you've ever seen someone in martial arts class and they chop through, punch through, kick through wood, that will happen to your robot. If some sort of sharp impact happens to the wood, it will shatter or break, similar to acrylic. However, wood can also change size when brought to a location with different humidity levels. This is very problematic, especially when you're going to competition, because sometimes you can travel a very large geographical distance for competition, and the wood within that robot can change its size by half an inch or an inch for each piece of wood, which can completely change the way your robot functions, sometimes even breaking the robot. This is all due to humidity. So this is the main reason why us at AvengerRobotics uses metal instead of wood, even though wood would arguably be easier for us to buy and to manufacture with. We just do not want to deal with treating over wood for humidity. Any questions? Final section, composite materials. So what are composite materials? Composite materials have become far more common in both robotics and engineering the last decade. These materials combine multiple other materials, typically using some material plus resin plastic, in order to make a material with improved properties. The two most popular composite materials in FRC are MDF board and carbon fiber. MDF board. MDF, or medium density fiber wood, packs together wood fibers and connects them using resin. Sometimes they'll use wax as well. Its uses are similar to plywood, but have many advantages. It is more consistent, so we don't have knots, which sometimes suffer in plywood or sheets of wood, where it would cause some weird inconsistencies in the strength of the wood. It has a smooth and flat surface, so you don't have to deal with the surface being bumpy or rough. It is just like it's smooth, it works, it's consistent. It is also less prone to changes in size between sheets. If a sheet is a certain size, you know it's going to be that size with this. The main disadvantage of it is its weight, as it's slightly more dense than plywood. So in the classes of weight, I would put plastics on top, they're the lightest, and then it'll be plywood, and then MDF would be slightly heavier than plywood, and then you'll have aluminum and then steel. Its main disadvantage is also that it's acceptable to humidity. So like how I said, plywood will expand and contract due to humidity. Think of that, but a lot worse. I would never recommend using MDF board in a final FRC robot unless you are treating it for humidity, which mostly is just painting it. And now we have the fun one. Every year we start to see more robots use this material, and I think it's really cool, and I really hope we can start using it more in the future, which is carbon fiber. Carbon fiber uses strands of carbon, the same element that makes up pencil lead and diamonds, mixed with resin. This material is ultra strong, ultra lightweight, and is gaining tremendous popularity in aerospace, cars, and most importantly for us, FRC. It is an almost perfect material for a robot. However, its main flaws are its price and difficulty to manufacture parts with. So we see a common consistency here where the parts of a robot that require really good materials typically are very expensive because the materials we need to use are extremely expensive. Materials that are good for FRC are also typically good for things that have a lot more money than FRC teams do, so they are good. I would put caveat there because the price is still better than titanium. So it's similar to titanium, but its price is better. So manufacturing carbon fiber. Since it is so difficult to manufacture, most of the teams would rely on outside businesses to make carbon fiber parts for them. This can also include, custom parts or tubes. So just like aluminum tubing, we can have tubes of carbon fiber that are already made and we can cut with, and that's highly recommended for teams that don't want to manufacture it themselves. If you do want to manufacture these in-house, you have two options. You can cut parts out of sheets, so you can get sheets of carbon fiber and cut them, or you can 3D print carbon fiber. And we'll put a caveat here as well, saying that there are technically ways you can mold carbon fiber by having the actual fibers and then painting resin on them. That is possible for teams to do. I won't go over that here. That's very advanced. So cutting carbon fiber. Carbon fiber cutting should either use a CNC mill or a Dremel. The Dremel is mostly used for small applications. For the CNC mill, you should use the strongest possible bit you have. So what I found is that you really want a carbide bit with diamond. This will just be an extremely strong bit. It will be likely not to break. You also want to be very careful with the dust. Try to use a combination of an N95 mask or respirator. No typical cloth mask for COVID. No, we're going to use an N95 or a respirator. Goggles, a vacuum, and a fume extractor if possible. You really don't want the stuff to get into your eyes. It's not toxic, but it is irritating, and you just don't want it. Better to be overkill. And now the really interesting one is 3D printing it. So you aren't technically 3D printing just carbon fiber, unless you have some crazy fancy machine I don't know about. But you can buy a carbon fiber and nylon composite filament that will allow 3D printed parts with maximum strength. Remember how earlier I said nylon was the strongest one? I lied to you. This is much stronger. However, your printer must be able to print nylon filament, and it is extremely expensive. To give you context, one roll of PLA filament is probably going to cost you around $15 to $20. One roll of nylon filament with carbon fiber is probably going to cost you $110. It is very expensive. I would say you should only need this filament if a high strength, and I mean high strength literally here, high strength mechanical part, and you must 3D print it. Or if you just have infinite money and like using new materials, you can do that too. support the FRC economy. Any questions? General manufacturing tips. So first things first, safety always comes first. You should always wear safety glasses at a minimum. This is not saying that you should only wear safety glasses. I'm saying that if I am on the team and I see you without safety glasses in the shop when you're cutting parts, you're in trouble. Wear safety glasses. Whenever you are manufacturing something, check to see the right tools, bits, and saws required. Luckily, most of us have access to the internet. If you're watching this online, I hope you have access to the internet. Otherwise, some crazy thing happened. You can always look up, how do I cut this material? What bits do I need? What blades do I need? If you don't have the ability to look it up, you can always ask a mentor or veteran on the team. Please don't use bits made for wood on metal. Don't use blades made for wood on metal. Don't do it vice versa. It's just going to damage and break the parts. It's very expensive. Please don't. And also, especially if there will be shavings or irritating dust, you should also wear gloves and an N95 mask or respirator. For shavings, the gloves are more important. For the dust, I would say the N95 mask and respirator is more important. But especially with the dust, you should probably do both. You don't want to cut yourself. That's what the shavings do. You don't want to get irritated. That's what the dust does. However, if you are using a more manual machine like a table saw, bandsaw, or miter saw, I'd actually recommend not wearing gloves. Even if the metal shards can technically cut you, the gloves at least have sometimes, some people have said this, make it slightly harder for you to know the location of your hand, and you might get your hand too close to the saw and whoops, no more hand anymore. At least you can probably get some disability pay in the future for it. Also, make sure you don't use a tool you don't fully understand. I will say this once again. Your team, if you're on an FRC team, has mentors and veterans for a reason. Ask them questions. Trust me, they've almost cut their hand off before. They'll tell you how to not do it again. And the last thing I want to emphasize again is keep different materials sorted neatly, especially if they look similar to each other. Acrylic and polycarbonate, please keep them separate. This is a speech from pain and suffering from my past. Any questions? All right, so final thoughts. This was the second to last lecture in this series, and I'm really happy with how it's gone so far. I can't wait to go over the last one, which I think is the most important one to me personally, which is design strategies and practices. You'll go over, how to CAD, what you're supposed to do with it, how to make parts nice and good for their manufacturing purposes. On this note, I really hope people have understood what this presentation is trying to say. People can now hopefully understand the different materials and manufacturing strategies for each material that we use in FRC. It is possible that there will be materials that you might use in the future that aren't on this lecture. If so, they're probably pretty rare. I'll just look them up. It's not too hard to figure it out. Anyways, I hope you had a good time learning in this lecture. If you are watching this online, I hope you finish the series off with the final video. If not, I hope you come to next Monday. Can't wait to see you guys again. Goodbye.